Well, welcome back to Data Skeptic and our continuing series on natural language processing. It really was the right time to do this series as we're at an interesting inflection point in this field. Over just recent years, we've been switching from more statistical, kind of plain vanilla machine learning based approaches to being almost myopically focused on the deep learning approaches, because they're working startlingly well. And the reason for that, of course, the availability of large corpora, the availability of commodity computer hardware and the right libraries and systems to do massively parallel distributed computation, and last but not least, due to the clever neural architectures that researchers are creating. So let's talk for a moment about what that takes. You're looking at something that's, at its core, mostly very simple algebraic transformations, tensor operations. And yes, I know to most listeners, the linear algebra might be a bit intimidating, but the underlying mathematics are quite simple. Sure, there's a few tricks for how you scale them up, some complicated terminology along the way, but more or less, the mathematics at work are the kind of operations that can be performed by someone with very menial mathematical skills. It's the arrangement of the components that really make the magic. How many layers you choose, what types of activation functions are at work, types of layers, how to make it residual, inclusion of attention-based mechanisms, a slew of other practices that are sometimes referred to as black magic. All these connections, these clever wirings, these greasings of the path that the machine learning will follow more easily. Each one of them is an optimization problem. We're fine-tuning towards some known goal. Well, known when it's the supervised case. More and more we're getting into the unsupervised areas of natural language processing. Predict the missing word. That's the basis of word2vec. But that missing word is still there, so maybe we ought to call that semi-supervised. Either way, there's an objective function, defining what that is, and how we measure our prediction against the expected value. Well, that's the core of all machine learning, really. So advancements in the field, they can be limited by the corpora available. More data seems to win. They can be limited by the availability of computation. Regardless of what you think about GP2 and its supposed controversy going on in the news lately, the estimate I heard was it would take about $45,000 to compute their pre-trained model. Most of us don't have $45,000 sitting around for little projects and experiments. And given the availability of, as I said, commodity hardware, it's almost as though there's an invariance between the computational limits and the financial limits you've got. So what's the limit of the architecture? Well, in a broad sense, it's how clever one is. Maybe you've got some new great idea about how to wire these things up, but we optimize them towards some evaluation function. So it's critical that we have good ways of measuring success. Some of these are deep down at that optimization layer, what type of gate we want, sigmoidal, arctangent, ReLU, leaky ReLU, these sorts of choices. But some of them are broader. The kind of tools that are going to be very important to us related to the topic of algorithmic interpretability. Even if the neural network or the code or whatever gets so complicated none of us can figure it out despite reviewing every bit in the system, if it truly is a black box, we still have a powerful mechanism of evaluating whether it's doing what it says it does or whether it's harmful or not. And that's the scientific method. We can take an empirical approach. So when the complexity of the deep learning system becomes a relevant part of the discussion, or the abstractness of the problem being attempted becomes a major factor, we'll require other diagnostics and metrics to look at the problems. And that's the sort of category that, in my mind, our topic for today fits into, and that's the Bleu score, BLEU, which is an imperfect acronym for Bilingual Evaluation Understudy. Not that great of a name. Not the worst, looking at you, ROC curve, but not the most self-explanatory name, so let's get a little bit into it before we do our interview today. Bleu seems to be the de facto standard way of measuring a machine translation system. After all, machine translation carries with it a very sticky problem. There's no perfect classifier known of right or wrong. No exactly labeled data set. The expressibility of languages and their structures and grammars and syntax, they're different enough that Although the same idea can naturally be conveyed in multiple languages, there's no one obvious correct solution for the English version of a famous French phrase or something along those lines. In fact, the best translators in the world, when independently asked to translate a passage, might come up with all different but all equally valid results. This makes evaluation quite complicated. So the 5-second answer behind what is Bleu is that it's a mathematical way of evaluating the quality of a machine translation system by comparing its results to a set of good examples produced by expert human translators. Alright, not bad for 5 seconds. Let's do the 20-second answer. Bleu is an algorithm, really, one that's simple to calculate, which is to its strength but also to its detriment. It first scans through looking at unigrams and saying, of the machine-translated sentence, how many of those same words appear in the reference translations, then bigrams and trigrams and so on. In this method reminiscent of the bag of words, how much agreement do we have? Okay, I think that was under 20. So the arithmetic I don't think is that important, or if it is to you, go find a research paper, Wikipedia, whatever. But if you walk away with one simple idea, is that Bleu is a means of evaluating machine translation. Now, it's not derived from first principles. There's no Peano's axioms at play here. It's just a nice technique that somebody came up with, and somebody else used it too. And somewhere along the ways, for lack of anything better, this is what people started using. And it's intuitive. It seems to do a pretty good job. The claim has been made, although I haven't gone deep into verifying this, but the claim has been made that when human judges are asked to evaluate the quality of a machine translation, their scores are highly correlated with the Bleu score. If so, that's a really good sign, if that correlation truly is strong. I'd like to know more about that. It's not that I don't trust it, just skeptical. And there's another skeptical side to this topic as well. For all the usefulness of Bleu, and by no means am I saying something crazy like abandon it, but let's pause for a moment and maybe evaluate how good it actually is. That topic is covered very well in a paper called Re-Evaluating the Role of Bleu in Machine Translation Research. And I'll be speaking with one of the authors today on the show about their evaluation of the Bleu score. Let's get right into it. Thanks to this week's sponsor, the Great Courses Plus. As you know, I love unpacking new information, even on the most complex of topics, and that's why I'm a big fan of the Great Courses Plus, a fantastic online learning platform. I can find lots of content that's interesting to me, from statistical design courses, artificial intelligence, data structures, and a really wide range of things like history and literature as well. These courses are taught by insightful professors who aren't afraid to dive deep. There are thousands of eye-opening videos and audio lectures. You can watch or listen on the go with the Great Courses Plus app, which I've actually tried and has like a nice syncing thing, so if you're going to be on a flight or something, it's great. This week I want to tell you about their course, An Introduction to Formal Logic. I'm sure you'll enjoy it because I really love formal logic. It's at the root of computation, and logic is a skill that can be learned. There's so many varieties of it, from modal logic to fuzzy logic. You can learn that and more, all on the Great Courses Plus, and this week we have a special offer. You can get a free month of unlimited access to the entire Great Courses Plus library. To do that, visit thegreatcoursesplus.com/data. Again, free month, unlimited access, nothing to lose. Check them out at thegreatcoursesplus.com/data.
My name is Chris Burch. I'm an associate professor in the Computer and Information Science Department at the University of Pennsylvania.
And can you tell me a little bit about the nature of your research?
Sure. I'm a researcher in the natural language processing community, so I work on several different topics. They're all sort of broadly related to natural language understanding. When I first started out in the field of NLP, I worked a lot with machine translation. So my PhD thesis looked at machine translation and a related natural language understanding problem on the monolingual side called paraphrasing. And I've helped to do a lot of things within the machine translation community. So I was one of the original co-developers of an open source package for machine translation called Moses, which allowed people to build statistical machine translation systems quite easily and had a lot of engagement with the research community, as well as some companies and government organizations. During the development of that, I also helped to run a workshop called the Workshop on Statistical Machine Translation, which is also called WMT. And I helped co-organize that for 7 years. And there, the focus was to try to evaluate the quality of a variety of different approaches to machine translation.
I'm not familiar with that problem. You mentioned paraphrasing. Could you tell me a little bit about it?
Paraphrase identification is trying to pick out sentences that mean the same thing within a single language but are worded differently. There's also the related problem of paraphrase generation, where you've got some idea that you want to generate a natural language sentence for, and instead of using a template, which could cause like very repetitive types of outputs, you'd like to produce varied outputs. So if you wanted to generate more interesting and fluent and varied outputs for something like Siri or Amazon Alexa, then you might want to invest in creating a high quality paraphrase generation system.
So in the time you've been working in the space, it seems to me machine translation has evolved quite a bit. Could you share maybe some of your thoughts on the evolution in our time?
So it's actually gone through several evolutions throughout my career. When I first started out, it was around the year 2000. I had recently graduated from my undergraduate program at Stanford University, and I went to work at an internet startup company whose goal was to scale machine translation to the web. We were repackaging a bunch of commercial off-the-shelf machine translation systems and trying to pick the highest quality ones for different languages. And then we built a big server farm to try to deal with web scale traffic. And at that time, most of the state of the art in machine translation was a rule-based approach where you would hire a team of linguists and language experts to manually handcraft bilingual dictionaries and transformation rules that account for the reordering that occur across languages and other things like morphology and so on. And so it was quite a labor-intensive approach. Around that time, an idea that had been introduced earlier called statistical machine translation was repopularized. In 1999, Kevin Knight, who was then at the University of Southern California, led a summer workshop at Johns Hopkins University where they implemented the IBM statistical machine translation models, very famous models in natural language processing. So they're called like IBM Model 1, IBM Model 2, IBM Model 3, IBM Model 4, which were data-driven approaches that took bilingual sentence-aligned parallel texts and were able to automatically align words in the foreign sentence with words in the English sentence, and then use those as the building blocks to then create a probabilistic model of how translation works. And then they had a decoding component. So given a model where you have a bunch of words and associated probabilities of their translations, plus other model factors like how many words a single foreign word should translate to when translating into English, and how they should reorder. Those model components combined produced the overall model that you then needed to, given a novel input sentence, decode and produce an output sentence. So this approach was called statistical machine translation, and it became popular around this CLSP summer workshop led by Kevin Knight, which had awesome participants like Franz Ock, who was the head of Google's machine translation efforts after he finished his PhD, and Noah Smith, who's now very famous in the field, but at the time was just an undergraduate participant. One of my friends from Stanford was another undergraduate participant, Michael Yar, and he showed me the final report from this thing, and I was pretty skeptical. At first, I was like, what does this have to do with linguistics? After I graduated and started working at a small company where we had a small budget and, a small team, I saw the value in being able to automatically create machine translation systems from data. And so I tried to convince my bosses at the time that we should do this ourselves. Instead of repackaging commercial off-the-shelf machine translation systems, we should do the research and build our own statistical machine translation system. So my bosses said no, and I decided that would be a good time to go off and do a PhD. So I moved to the University of Edinburgh and started doing research into machine translation. And I even got a small grant from the Scottish government to commercialize research in statistical machine translation, which was awesome because at the time I was a PhD student, I had 2 full-time software developers, which I think is pretty unusual for a PhD and pretty awesome.
Yeah.
That was fun because I got to do lots of hands-on development of machine translation. Of course, a couple years down the line, Google came along and started giving away their statistical machine translation systems for free. So that undermined the business proposition of that. Yeah, and then for several years, statistical machine translation and its variants were the dominant approach. So we had the original IBM-based models, which were essentially a word-based approach to statistical machine translation. And then Philip Cohn and Franz Ock and several other researchers developed phrase-based approaches to machine translation, which reused larger chunks of human-translated text and produced much higher quality output. And then we had interesting approaches to hierarchical phrase-based machine translation by David Chang, and then later more syntactically informed statistical machine translation. So there were many iterations of this idea of a statistical data-driven approach to machine translation. Over the past few years, we've shifted from that kind of approach to a neural network-based approach. So now the current dominant approach to machine translation is called neural machine translation. And the idea is similar in that it's a data-driven approach, but instead of having what are essentially tables of phrases and their associated translations and probabilities, we now have a continuous space model of translation. So there's lots of really interesting research, like the Word2Vec program that you've talked about on your podcast before, where you're able to build a vector space model of semantics. And that same sort of vector space model of semantics is now leveraged in neural approaches to machine translation.
So before we get into the meat of our topic today, I was wondering, even though I've covered a little bit on the show what Bleu is, could you share a high-level definition of what this metric is and why someone would want to use it?
Bleu is an acronym that stands for Bilingual Evaluation Understudy. And it was developed by IBM in the early 2000s to evaluate machine translation. So the reason it's interesting and important is that the automatic evaluation of translation quality is actually a super challenging research problem unto itself. You can draw an analogy between trying to do something similar, like evaluating the output of an automatic speech recognition system, to evaluating the output of a machine translation system. And then you can see that the challenge of doing machine translation evaluation is actually much, much harder than trying to evaluate the output of an automatic speech recognition system. So in ASR, you have a single authoritative transcript. That means that the speech signal can really only be transcribed in a single way. It's linear, right? So you have the order of the words exactly as it appears in the order of the speech signal. But for machine translation, you can have many alternative ways of translating the same input foreign sentence that are all equally valid. So you have lots of alternative lexical choices that you could make, many of which are equally good. And unlike the speech signal, which comes in a particular order, you can move a lot of the clauses around. There's no single right answer to what constitutes the correct translation. So what Bleu was trying to capture is those two elements. How can we capture the allowable variation in translations? So the way that Bleu approached that was, instead of taking a single human-created translation as the reference, it allowed you to create multiple references, all produced independently by different translators. And then instead of requiring that all the words occur in a single order, it looked at shorter phrases. So that means that if you matched a phrase, which for Bleu's purposes tended to be sequences of words up to length 4, then you could move those around and you got credit if you got long chunks, but there was no strict order imposed on the words other than the order that implicitly gets defined by tiling together a bunch of sequences of length 4.
The success of a lot of the modern techniques, as you said, have been data-driven, and the more data, the better seems to be the case, at least in general. With that in mind, it seems to me that having many translations could be even more prohibitive to having a nice training set. Could you speak a little bit about how that challenge works out for researchers in practice?
Oh, yeah. So this notion of how we build machine translation training and evaluation sets is actually a pretty important one. The idea behind Bleu is we can hire a bunch of independent translators to all translate the same foreign sentences into English, if that's our direction. And then we get this notion of here's the distribution over possible translations. So we capture that allowable variation in translation. But in practice, that's actually pretty hard to do. The number of evaluation sets where we actually have multiple references is pretty small. Most of the time, they're ones that are created by NIST, the National Institute for Standards and Technology. So NIST runs a lot of machine translation evaluation competitions for government-sponsored research, like in DARPA programs. There's actually very few machine translation evaluation sets that have those multiple references. So what's typically done is researchers will take their set of training data and split it up into training, development, and test sets. The test set and the development set, which are the pieces that you really want the multiple references for, don't actually have multiple references. For most machine translation research, you only have a single reference translation available. Although Bleu allows you to capture this variation in translation, most of the time that's missing.
From just a high level, or if I think back to when I first learned about Bleu, the most concise way I can describe it is it's intuitively appealing. It doesn't seem outrageous. It seems like a nice idea. But let's get into some of your criticisms now. Tell me a little bit about some of the ways you considered in which Bleu might not be the ideal metric.
So actually, first let me say a few things that are good about it before I break down why it's bad. So you're right that it is intuitively appealing. It did help to advance the field in several dimensions. So one is the basic notion of why we want automatic evaluation metrics to begin with. Human evaluation of machine translation, which is probably ultimately what we want, or task-based evaluation of machine translation, if it's going to play a role in a larger pipeline, tend to be very expensive and cumbersome to perform. So having an automatic measure of translation quality is actually super useful. Being able to run a lot of different experiments and compare a lot of different approaches to machine translation or a lot of different variations on your own model is actually super important. One thing that it allowed us to do was to optimize model parameters. We have this development stage where we have to do things like put a balance between how much we're going to trust the translation model component of a machine translation system versus the language model component, how much we're going to weight each of those, being able to decode a lot of sentences or translate a lot of sentences using our system, automatically evaluate the goodness of our model under different parameterizations, and then update our model's parameters based on what settings produce the best output is super important. And it led to much, much higher quality machine translation than we had prior to this. That's the good reason for Bleu. So it's an automatic evaluation measure that is much lower cost than human evaluation, and it allows us to tune our system parameters automatically.
Yep, all positives.
Yeah. So the things that I was critical of in the paper was it ought not to be a complete substitute for human evaluation. It's really just designed to approximate human evaluation. And in fact, in the original Bleu paper, they did a nice study, which was relatively small scale, but quite reasonable at the time, to evaluate the correlation between the predicted translation quality from the Bleu metric versus the human-judged translation quality of several systems. This is actually the most important aspect in the validity of using an automatic measure to report the scientific results in a paper, right? So if you want to present a paper where you say, my new model for machine translation is better than some existing model, you need some evidence to back up that claim. And a lot of people use Bleu as the evidence that my model is better than the existing state of the art. And so that relies on the presumption that it's going to correlate well with human judgments of translation quality. In running the workshop on machine translation, over time we've gathered tens or hundreds of thousands of judgments of translation quality from human judges where we're comparing a variety of different systems. One of the things that we noted in our critique of Bleu was that Bleu is actually biased towards a particular style of model. And that happened to be the model that was making the most progress at the time, so it went undetected for a while. We did a plot where we compared the human score of translation quality against the Bleu score for two types of systems. One was the older style rule-based machine translation system versus the more contemporary phrase-based statistical machine translation. We were able to create several instances of the statistical system just by changing the amount of data that we trained it on. And so, like with any other machine learning problem, if you train it on more data, it tends to do better. So that was reflected in the Bleu score. So you could see that the statistical machine translation system trained on a smaller amount of data had a lower Bleu score than the one trained on a much larger amount of data. And that same directionality held in the human judgments. So the one trained on more data seemed to be better to people. But the Bleu score for the rule-based system was very low. So it was even lower than the small training set for our statistical machine translation system, the one we kind of intentionally handicapped. But the human scores for the rule-based system were comparatively high. The rule-based system was performing almost at the same level of the state-of-the-art phrase-based statistical machine translation trained on all of the data. But this wasn't reflected in the Bleu score. So the rule-based system was penalized by Bleu, even though human judges thought that it was actually pretty good. If you unpacked that, you could see why that was the case. So the rule-based system was working really hard on things like getting the grammar right and subject-verb agreement or grammatical gender or things that might have longer distance dependencies than those. But the statistical machine translation system, especially the phrase-based statistical machine translation system, was producing very fluent output if you looked only at the phrase level, like only at the immediately adjacent words, because those are the building blocks that it was using. And those were the things that it was being graded on by Bleu, right? So Bleu has this n-gram-based precision metric, so it's matching how many sequences of up to 4 words match the reference translations. So it's really only looking locally and not at these larger grammatical structures. The result of that is bad for science, right? Like that's super bad for science. If you want to report your model score, if you want to report that you built a better model, then you need a metric that can reliably reflect that. So you don't want to say, hey, my statistical machine translation system vastly outperforms this old state-of-the-art rule-based system according to Bleu, when in fact nothing is happening on the human judgment side. Conversely, you don't want to get discouraged if you've invented a brand new model that incorporates really sophisticated things like long-distance dependencies and grammatical relations that Bleu simply isn't capturing. So if you find that your new syntactically informed model is not showing an improvement in Bleu score, that could just be because it's doing something that isn't well reflected in what Bleu is picking up on. And it could mean that even though you're showing no improvement in Bleu, your model is still making improvements to the translation quality. So that's the kind of flip side. So either you're fooling yourself into thinking your model is actually better when it isn't, or you may have no detectable change in Bleu score, but you might still be producing interestingly better translations that simply aren't detectable by Bleu.
Do you have any thoughts on alternatives to Bleu, or have alternatives emerged since the points in your paper were brought to the forefront of the research field?
Yeah, so we ran this annual evaluation campaign called the Workshop on Machine Translation, WMT. We did a NIST-style bake-off where we had initially a shared task where we were inviting researchers from all around the world to translate the same test sets that we produced using the same training data that we provided to everyone so that we could do a fair comparison of different approaches to machine translation. And the first year that this was run, it was run by Philip Cohn and Christoph Muntz, and they just evaluated the system outputs using Bleu. The next year, we did a human evaluation, and we were able to analyze how well the systems held up against each other using the human scores. And then subsequent to that, we started a new shared task where we said, we've now got all these machine translation outputs, and we've got all these human judgments of how good all of the outputs are. So let's put a challenge to the research community and say, why don't you try to develop a better machine translation evaluation metric? And we'll measure it based on how well it correlates with the human judgments of our translation quality. Over the years, there have been many, many approaches, none of which have had quite the same traction that Bleu did, but some of which have actually done a better job and had higher levels of correlation with the human judgments than Bleu had. Some of which take into account interesting linguistic features, like they'll parse the system output and the reference translation and do a comparison of the syntactic structures produced by the two systems. One even did a textual entailment test. So there's an interesting task within natural language understanding to say, is this short sentence logically entailed by this long paragraph? So one researcher who was then a postdoc at Stanford named Sebastian Pato applied this recognizing textual entailment software to see if the output of the machine translation system entailed the reference translation. And lots of interesting, more sophisticated approaches than just n-gram precision were developed as part of these shared tasks to see who could develop the machine translation evaluation metric with the highest correlation. Probably the most widely used one outside of Bleu is one that was developed by Alain Levy and his PhD students at Carnegie Mellon University called Meteor. And it had an interesting variation where instead of relying on multiple reference translations to produce the allowable variation in translation quality, it directly incorporated a model of synonymy or paraphrase. It would give a model credit if it got close to what the reference said. So it would use things like WordNet synsets, which are a bunch of synonyms for a word, or it would later use a model that I developed for paraphrasing to try to capture phrases that were similar to the reference translation. And then there was another evaluation metric that got a lot of traction called translation edit rate that was developed by Bonnie Dorr and her PhD students at University of Maryland. And the TER metric had a nice property, which was it was a lot more interpretable than Bleu score. One of the problems with Bleu score is it's hard to think about what it means. It's just a number where higher is better, but unlike things like word error rate in automatic speech recognition, you can't have some mental arithmetic to say, oh, that means that I'm missing 1 out of every 10 words or something like that. It's just not easily anchored in the same way. Translation edit rate was much easier to do that with. You could kind of do that same mental arithmetic and see what fraction of the words you were getting incorrect.
So I'm curious if your current research and work requires a metric like Bleu, and if so, what are you using?
So yeah, it's easy to critique Bleu, but it's hard to get away from using it, I have to say. Partly it's become enculturated. It's part of the academic culture of publications in this field that we use it now. It is the benchmark. It's the standard metric. I've done some other research to try to build other ways of evaluating machine translation. At some stage in my career working on machine translation, I got really interested in crowdsourcing as a way of collecting translations for languages that we don't have much training data for data-driven approaches to machine translation, like statistical machine translation or neural MT. And that took me down a long path of crowdsourcing and using services like Amazon Mechanical Turk to have humans in the loop. I've done a bunch of interesting experiments with having humans directly evaluate things like translation quality. Now it's super common practice for me and anyone in my lab, if we have an idea and there isn't a standard evaluation metric, or if we think the improvements that our model is making won't be accurately captured by the standard evaluation metric, we use Amazon Mechanical Turk and crowdsourcing to create manual evaluation of our model output. In one of the very first papers that I wrote looking at the usefulness of Amazon Mechanical Turk to evaluate translation quality, I recreated an interesting experiment that had been run by Doug Jones, who's at MIT Lincoln Labs. He looked at using a reading comprehension exam given to military linguists by the Defense Language Institute. So it's a reading comprehension test that military linguists take in order to get a grade, and that implies what duties they're allowed to do. like how proficient they are implies what tasks they can actually do for the military. So the interesting thing that he did was to take one of these defense language exams, run the foreign language texts through a variety of different machine translation systems, and then have monolingual English speakers take the exam using different machine translation outputs. And there he could quantify in a really interesting way, like how much better was this system versus that system. And it had this anchor point to say, this is the score that this system would have gotten on this military language proficiency exam. That I think is particularly awesome. Like it's a really interesting way of trying to evaluate machine translation that gets at one of the important questions that you want to know whether it's answering. Like, is it allowing you to understand the texts? And if so, at what level? But it's very hard to get your hands on this kind of high quality reading comprehension test of a foreign language. So I used Amazon Mechanical Turk to build a bunch of reading comprehension tests where we showed them the reference translation created by a human of a complete article. We asked them to write reading comprehension test questions, and we gave them guidance on what made a good reading comprehension test question. And then we asked the workers to provide sample answers. We then had a second round where we had, once again, Mechanical Turk workers vote on which of the questions were the best and weed out questions that implied the answers to other questions. And then we did a large-scale study where we took a bunch of the system outputs from the workshop on machine translation and had Turkers take the reading comprehension tests that other Turkers had designed. So they would see the output of a single system, the questions that had been posed and selected as part of the earlier stage of the development of the reading comprehension test, and then they answered them. And then because these are free-form answers and not multiple choice questions, we had to grade them. So we did yet another layer of workers on Amazon Mechanical Turk who saw the original article, the question, the sample answer, and then a collection of answers that other workers had created based on different systems outputs. And they said, this is correct or not correct. So the whole end-to-end pipeline was done via crowdsourcing. Like they designed the reading comprehension test questions, they selected the best ones, they took the exams using different machine translation system outputs, and they graded it. The whole end-to-end system was done using crowdsourcing, and it came at like a surprisingly low cost.
Very neat.
So that's one way that I've tried to get around the deficiencies of Bleu, like much more interesting and more creative ways of evaluating system outputs.
Yeah, well, that raises an interesting hypothetical in my mind, sort of an unfair question, but I'll ask it anyways. One of the ultimate things we're after, I guess, in NLP in general, or maybe just in computer science, is can we get a machine to pass the Turing test, the imitation game? Do you think ultimately getting human-level translation is an equivalent problem? Do we need some sort of AI, or will we solve human-level translation before we solve the imitation game?
Clearly, they're related, right? So you could suppose that in order to solve the Turing test or to win at the Turing test, you need a genuinely artificially intelligent agent who's capable of understanding what the other person is saying and responding intelligently to it. The same thing seems to be happening in machine translation, right? You have to understand the foreign language text, seemingly, in order to be able to translate it. But I feel like for machine translation, there's much more of a direct signal, like input to output production than there is in genuinely understanding what a conversational participant is saying to you and what constitutes a good response. So there's actually like a lot of interesting work in trying to build chatbots, reusing many of the same models that we use for neural machine translation, where we have a bunch of input sequences and we want to learn what are appropriate output sequences. Instead of just taking foreign language input sequences and generating English translations as the output sequences, a lot of researchers have looked at taking things like one turn in a conversation and trying to produce the next turn in a conversation. And they train these models on things like movie dialogues, where you have one character and then the response to that character, or you have all Twitter conversations and you have what someone says and then what someone else says in reply to that. And you can use the same models to have the same sequence-to-sequence training and learning that you'd have in machine translation. it seems like currently the quality is not as good as machine translation. And I don't know exactly why that is. I suspect that oftentimes it's due to things like maybe the training data that people are using is not actually high quality enough. Mm-hmm. Or if you had the same volume that you had for machine translation, like for some languages like French English, we have almost 1 billion words worth of training data available to all researchers and not just companies, then maybe you would have higher quality chatbots. But so far that same strategy hasn't panned out as nicely for dialogue systems as it has for machine translation systems. And interestingly, the same problem exists for dialogue agents and chatbots as it does for machine translation systems, right? So a lot of research in dialogue systems and chatbots has used Bleu as an evaluation measure. And there, it's terrible. I think that's a terrible use of the Bleu score because there are many, many different ways that you could respond to a prompt. And once again, just like the situation that machine translation researchers found themselves in, people who are developing chatbots only use a single reference, right? So they only use a single response, and what they're measuring is almost nothing. I would be super surprised if someone did a study that found any strong positive correlation between Bleu score and human judgments of chatbot response quality. But it is an automatic measure. It's better than just the probability under the model. So people use it because it's there.
Well, Chris, where can people follow you and your work online?
If you're interested in taking a look at any of my publications, you can find me at the University of Pennsylvania. So I have an easily Googleable name. Chris Gallison Burch will take you to my publications page, and you can find all my work there. I'm not very active on Twitter, but if you want to follow me, I'm at CCB on Twitter. Easy to remember.
Sounds good. Well, I'll have links to all that stuff in the show notes, as well as some extra stuff like the Moses package you mentioned. Chris, thank you so much for taking the time to come on the show and share your expertise.
My pleasure. Thanks for having me.